What we're going to study now is called the method of undetermined coefficients. The idea for this method is, I'll be completely honest, it's guess and check. But it's an intelligent guess and check, and that's important. That is the big distinction between mathematical thinking and just sort of genetics. Doing mathematics by a genetic method is a very poor way to do it, where you just keep trying one thing after another, and whatever doesn't work gets selected out until you eventually come up with something that works. You want to be able to have something that guides you towards the right idea. The concept of undetermined coefficients is what happens when we're trying to solve a differential equation that is non-homogeneous. So let's say we had y prime minus 2y is equal to x minus 2. Well, let's make it plus 2, make it a little bit more interesting. All right, y prime minus 2y, if that was equal to 0, I can solve it. Okay, and as a matter of fact, I should. Because if I have a function that can make this into y prime minus 2y is equal to x plus 2, call that function f. And I have another function, call it g, where y prime minus 2y is equal to 0. Then f plus g, if I plug that into there, that's still going to be a solution. It's still going to give me x plus 2. All right, so let's begin by solving y prime minus 2y is equal to 0. Well, we've done this one. We've done it a bunch of times already. Hopefully you've done your homework on this, and you know that this gives you y is equal to any constant times e to the 2x. All right, so this is the solution to the homogeneous system. Now, to solve this, well, I don't have an obvious method. I can't just take an exponential and hope that this is going to work, because exponentials aren't going to give me polynomials popping up out of nowhere. However, if I had a polynomial, odds are good that with the derivative of a polynomial minus the polynomial itself, well, forget about odds are good, necessarily that's at least going to be a polynomial. Maybe I can adjust it so that it will give me x plus 2. Okay, so that's the intelligent part of it, the intelligent part of the intelligent guessing. We look at the function and we say, what kind of a function could be a solution, could reasonably be a solution. So let's let y be equal to, if y is just a constant, that's not enough. I'm going to have the derivative of a constant is 0 minus a constant, that's just a constant. So I want y to at least have an x somewhere in it. Let's take y is equal to ax plus b. If I choose that, then the derivative minus the function is going to give me a linear function. And if it gives me a linear function, that's fantastic. That's exactly what I want. If I had gone higher, if I went with a quadratic polynomial, then y prime minus 2y would be a quadratic polynomial. And that's more than I need. Now, it'll fix itself very quickly because the coefficient for x squared is going to have to be 0. But this aspect of it, of this method of undetermined coefficients, the idea is, let's come up with what is the most efficient way to find a solution. So this over here makes the most sense. We begin with y is equal to ax plus b. That means y prime is equal to just a. And now we can try to solve. Y prime minus 2 times y is equal to a minus 2 times ax plus b. And so we have negative 2a times x plus a minus 2b. And this right here we want equal to x plus 2. All right? We can create a system of equations, try to solve it. They're all going to be linear. It's pretty straightforward. Generally, we don't need to. When we're dealing with polynomials for y, it's almost always set up for what most linear algebra textbooks call back substitution. You'll be able to solve for one of your coefficients immediately, and then you'll go on from there. So we can compare the coefficients over here with the coefficient of the x. There isn't anything written, that's because it's just 1 times x. So that means that we have negative 2a is equal to 1, and therefore a is equal to negative 1/2. We go over here, the constants need to be the same, and so a minus 2b is equal to 2. Well, a is equal to negative 1/2. I can solve it immediately. Negative 1/2 minus 2b is equal to 2. Therefore, b is equal to, we'll bring the 2b to the other side. We're going to have negative 5/2 over there. Divided by 2, it'll become negative 5/4. Okay, so let's put these two solutions together. All right, we want to take what we have for the y, a particular value of y that solves this equation, and then we want to add the value for y that solves the homogeneous system. What I'm going to end up with is y is equal to, first of all, the homogeneous part, c times e to the 2x, plus that bit over there that we have on the bottom left, we refer to it as the particular solution. Right? We're using the same terminology that is used in linear algebra. So we're going to have negative 1/2 times x minus 5/4. And so in general, we refer to this part of it as the homogeneous part, and this as the particular part. And the way that they're defined is that y prime or yh prime minus 2 times yh, that's equal to 0. The particular solution, when I plug that in, I'm going to get x plus 2. And so if I let y be equal to any constant times yh plus yp, then when I try to work with this, y prime is pretty straightforward, and y minus y prime is going to be equal to c times yh plus yp. I'm rather curious why I've decided to solve this in particular. Let's make it the actual equation. There we go. Y prime minus 2 times y. So that's going to give us c times yh prime plus y prime p minus 2 times the function itself. Collect like terms. Collect the homogeneous system together, or solution together. Collect the particular solution together. And we are going to have c times something which we have already said is equal to 0, plus something else which we have already said is equal to x plus 2. For x plus 2. So that's going to serve as a solution. What is happening here is simply a little bit more of the standard linear algebra pervading all of calculus. We are looking for just the homogeneous solution, the one that's going to solve the answer if we replace the constant bit, the constant type, f of x, if we replace it with a 0, and we are looking for just a single solution for the particular question, for having f of x be non-zero. And then the combination over there will solve any differential equation of this form.